Welcome to the physics class for February the 2nd. So as usual, couple quick announcements before we get into the physics. So first thing is you may have heard from your other teachers that Principal Wilson has signed all of us teachers up for some conferences next week. They're going to be held over Zoom, but they're going to be held during the daytimes when we would normally be teaching. So we are not going to be able to do live teaching next week. Everything's going to have to be stuff that we put on Canvas, and then you guys just log on to Canvas and do it on your own without live help from us. And that messes up my plans for the test. I was going to give you guys a test next week, but I need to supervise the test. So yeah, I guess I'm going to have to push the test back, and I will come up with some other activities for you to do next week, and they will be good activities. I have some ideas on what I'm going to do, and it's going to be time well spent. You will learn a lot from doing it. It's not just going to be make work type stuff. So anyway, yeah, the test is going to be pushed back. Other stuff. Okay, tutoring. Please don't forget about tutoring. So after school, Tuesdays, Thursdays, and then during the day on Friday and Saturday as well. Please attend tutoring. And other than that, I can't really think of any announcements. So let's go ahead and jump into last night's homework. So there. Okay, so here are the answers to the ones that you haven't already looked up in the back of the book. As usual, if you could only see one problem worked through, what would you like that one problem to be? And hopefully we'll get two problems, but we might only get one. So let's see what that one would be. All right, I'm seeing 10 and 4, but I'm not seeing very many votes yet. Let's get a couple more votes in. The rest of, okay, so 10 again. All right, so it looks like a lot of people had questions about 10. And okay, that's it. So 8 or 10. All right, so it looks like the winners are 4 and 10, with 10 getting the most votes. So let's do 10. And then if we have time left over, we'll do number 4 as well. Okay, so number 10. Here's my glasses. Oh, I'm dead without my glasses. Here they are. Okay. All right, so okay, so we got somebody playing a musical note. We want to know how fast we'd have to be going to get it to be a higher note. Okay, looks like a worthwhile problem to do. Let's open up a whiteboard. Okay, so this is a Doppler problem, obviously. So let's start by just writing what the Doppler equation is. The Doppler equation says that the detected frequency is equal to the source frequency times V minus VD over V minus VS. Okay. All right. I don't expect you to have that memorized. When we take the test, you can have it on your cheat sheet or look it up or whatnot. But I'm thinking that if you did all of the homework problems last night, you used this equation so much that you probably have it memorized. All right. So they are telling us what the source frequency is. They are telling us what the detected frequency is. They are telling us what number to use for the speed of sound. And by the way, that number is 343. So get used to that. That's the number for the sound in air if the air is at room temperature. So this is the number we're going to be using more than anything else. They want us to calculate what the velocity of the source is. So that's what we're supposed to calculate. Now, they haven't told us what the detector velocity is. And so that could be a problem. The only way that I can think of to solve this is we're just going to have to make an assumption. We're going to have to assume that the detector is not moving, because otherwise this problem is unsolvable. Okay, so that might be what threw most of you off, is there's no way we can solve this unless we make the assumption that the detector frequency is zero, or velocity is 0. Okay, so from this point on, it's no longer a physics problem. Now it's just a math problem, and you're going to math, right? All right, so let's see. So we want to solve for VS. First thing I do here, let's clear up a little room here. So give me some room to work. All right, so this is just an algebra problem, really. Let's multiply both sides by V minus VS. Okay, so that goes away. And then let's distribute this guy out to both of those. So we're going to get is FD times V minus FD times VS equals FS times V, right? Double check me here, make sure I don't make any silly algebra mistakes. I think we're good. Now my V looks like an R, but that's a V. All right, and remember, we're trying to solve for VS. Okay, so what I'm going to do is I'm going to swap places with these guys just so that way I don't have a minus sign in front of the term that has the VS in it. All right, so if I do that, so I'm going to have FD times V minus FS times V equals FD times VS. Divide both sides by FD. Okay, and so now we get VS equals that. All right, so now it's just plug and chug. So they tell us that the detected frequency is 271 and the speed of sound is 343. So room temperature, and that's also there. The source frequency they tell us is 262. And then again, that's the speed of sound there. So now it's just plug and chug from this point. So I'm thinking we're good. So if we plug and chug correctly, we should get 11.4 as our answer. Does that answer your questions? Okay, I'm not hearing no, so I'm going to assume yes. All right, so I think we have enough time to do problem number 4 as well. Let's go take a quick look at number 4. So number 4 says okay. Those of you that got the wrong answer, I'm willing to bet that I know what you did wrong. And I warned you about this one. Okay, so we shout across the canyon and we hear the echo 0.8 seconds later. Okay, so here we are. Okay, here's the canyon wall. So we're shouting over there, the echo bounces back. So the time that it takes till we hear the echo is 0.80 seconds. And now they don't tell us what the air temperature is. Okay, so if they don't tell you what the air temperature is, you can assume that it's room temperature. That's a good safe rule to go with. All right, so room temperature, hopefully you recognize in Celsius is 20 degrees. That's room temperature. So when you look on the table there, you find out that the speed of sound for air in room temperature is 343 meters per second. Now that's assuming room temperature. That's also assuming you're at sea level. We are not at sea level. So it's gonna be a little different for us. In fact, that's what I'm thinking of having you guys do next week, because I'm gonna have you do an experiment where you measure the speed of sound. And don't be surprised that even if you do it at room temperature, you're gonna come up with a number that's a little different because we're not at sea level. We're up here in Utah, which is a pretty high altitude. And so the speed of sound for us is gonna be a little different. But let's assume we're at sea level. Okay, so we're going to use distance equals rate times time. And so that's the speed that the sound wave is traveling at. This is the time that they gave us. When we do that, we're going to get a number, and that number is not going to be 140. Why not? The number that we're going to get is going to be 280. And the book says the answer is 140. What went wrong? We talked about this last time. Do I have to pick on somebody?
The wave has to travel there and back.
Very good. That's exactly it. This distance that we get from this equation, that's the distance that the sound wave traveled. And the sound wave went to the cliff and back. So they're asking us how far away the cliff is. So we have to take whatever number we get from this equation and we have to divide it by 2 if we want to know what the distance to the cliff is. Okay, so this is a super common mistake. No matter how many times I warn people not to make this mistake, they go ahead and they make it anyway. Okay, so please don't make this mistake on the test, okay? You got to read the question and make sure you understand what they're asking for. They're not asking what distance did the sound wave travel. They're asking what is the distance to the cliff. Okay, now the other one that I wanted to talk about, let me just take a minute here. Question number 14. I'm surprised that none of you asked about that because every year I always get questions about that. So what's happening here is they're talking about pressure level. And that's not any of the words that we use. Now, when we were talking about decibels, we came up with 3 rules that you can use for knowing how much of a volume increase it is. Okay, so remember, if we make a graph here, so each one of these steps in this graph is 10 decibels. So let's say we start at 30, and then we go to 40, and then we go to 50, and then we go to 60, and dot, 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 dot. Okay, so if you go up 10 decibels, so it means you start at 30 and you go to 40, or maybe you start at 60 and go to 70. So if you go up by 10 decibels, how much has the quote unquote loudness increased? Well, it depends on how you define loudness. So there were 3 different ways that we defined loudness last time. So one way is we talked about the power that is delivered by the wave. And that is the one that that physicists used when they came up with the actual equation for decibels. That one was the one that involved the power. Okay, so the rule, if you're talking about power, is that every time you go up 10 decibels, that corresponds to a 10x increase in the power. So for each 10 decibels, okay, every time you go up 10 decibels, that would be a 10x increase. Now, the other way that we talked about it was maybe you're not worried about power. Maybe what you're worried about is the amplitude of the wave. Okay, and amplitude is the square root of power. And so for every 10 decibels that you go up, if you're talking about amplitude, that would correspond to a square root of 10x increase. And then the third way that you could measure loudness is in terms of perceived loudness. And that depends on the response of the human ear. And the human ear works out that it's approximately 2x, maybe not exactly, but for good enough approximation, for every 10 decibels that you go up, that would correspond to a 2x increase in the perceived loudness. Okay, so when you look at problem number 14, you'll notice they do not use the words power or amplitude or perceived loudness. They use the word pressure level. So what is that? Well, pressure level corresponds to the amplitude. That's the thing that you need to know. Okay, so when they're talking about how much does the pressure level increase, they're talking about the amplitude. All right, so on problem number 14, where do they start and where do they end? Let's see, how many decibels do they start from? Here it is. Okay, so they start at 50 decibels and they go up to 110. So there's 70, 80, 90, 100, and here's 110. And by the way, somebody just arrived, so hang on, let me let him in here. Don't want to keep him in the waiting room. Let me go ahead and mark him tardy. Okay. All right. So now that we know that we're talking about amplitude, okay, so that, whoops. Okay, you got to remember whenever I make any changes there, I have to turn my annotation off and on. Okay, so 50 to 60, that's the square root of 10. 60 to 70, that's another square root of 10. So basically what that means, every 20, that corresponds to 10. So there's 10, here's another 20, so that's another 10, here's another 20, so that's another 10. So what we got is 10 times 10 times 10, so that corresponds to 1,000. All right, so the pressure level or the amplitude of a sound wave that is 110 decibels, that has an amplitude that is 1,000 times greater than a sound wave that we would measure out to be 50 decibels. Okay. So remember these 3 rules and you'll be good. Okay. And I think that's it for last night's homework. Unless there's any questions, I'm going to go ahead and move on. So any questions? Going once, twice, sold. All right, let's talk about new stuff. All right, so today we're going to continue on in chapter 15. We are not going to have enough time to do everything. So what we'll do is today we'll do what I call 15B. Next time we meet, we'll do 15C. And then after that would be when we could take the test, but because of this weird conference that we have to attend, I'll have you do some other activity instead. All right, so 15C or 15B, basically what we're going to do today is we're going to talk about music. Okay, so sound is just a combination of any type of sound that's hitting our ear. We call it sound, but music is a special subset of sound. That's when we have special tones that we find especially pleasant. So that would be music. Okay, so what I'm going to do for you right now is I'm going to play my favorite musical instrument, a Coke bottle. Okay, and the reason it's my favorite musical instrument is because it's finally something Aurora understands. Okay, the reason it's my favorite musical instrument is because it's so simple, right? Now, you guys have all done this, I'm sure. So what I'm going to do is I'm going to blow across the top of the Coke bottle, and if everything goes right, then one musical note is going to resonate. Now, generally, when I do this with nobody looking, then it works great. But if I try to do it when people are looking, then it doesn't work. Okay, so let's see if I get lucky. Here it goes. There, I got it on my second try. All right, so you all heard that, right? Let's try that again. All right, so I got a musical tone that resonated. Now, what's actually happening here? A physicist and a musician, yes, and a sailor. Okay, so let's open up a whiteboard and let's see if we can figure out what's happening. So here's the bottle. And you may have noticed I've got a little water in the bottle. That's important. We're going to talk about that later. All right, so what I'm doing is I'm just blowing across the top of the bottle, and yet a musical note is coming out. So what's the deal? What's happening? Well, when I blow across the top of the bottle, in this that I do, that actually contains a whole lot of frequencies. This that I do contains some high frequencies, it contains some medium frequencies, and it contains some low frequencies. All of those are contained in that I'm doing, but one of those and only one of those is going to match the natural frequency. So it would help if I could spell natural. Let's try it again. So the natural frequency of the bottle, okay? So what do I mean when I say natural frequency? Well, it depends on how much water I have in the bottle. Okay, so what I'm going to do now, so I've got a little basin here. So I'm going to play my musical instrument, and I want you to note, I want you to take careful note of what tone, what musical tone do you hear? And then I'm going to pour some water out and I'm going to do it again. And so notice how that works. So here goes the note at the original water level. Okay, now I'm going to pour some out. Here goes again. You notice pretty noticeable difference there, right? So when I changed the water level, it changed the natural frequency, which changes the which musical note is going to resonate. So when I was blowing across the top here, I wasn't blowing any different the second time than I was the first time. I was blowing exactly the same. So if we look back at my drawing here, okay, so what you're seeing across the top here, so this is me going across the top. So I did it exactly the same the second time that I did the first. The thing that's different is that out of this combination of random frequencies, one of those and only the one of those resonates. And when I poured out some water, then the column height changed. And so that changed the natural frequency. And so that meant that a different one of those random frequencies ended up resonating this time compared to the first time. All right. So this is something that you need to understand. And I think probably the best way to understand it is to play with one of these online simulators that I put on Canvas for you. I put several of them on there, and I hope that you guys did play with those. I did specifically ask you to play with those. So the one that I'm going to play with right now is this one up here, is the Online Wave Reflection Simulator. Okay, so if I click on it and wait a little while. Okay, so this should look familiar to you. This is the one that we played with last time. And remember how I specifically asked you to please play with this thing? And I said, please experiment with all settings, but there was one setting that I was especially interested in. I wanted you to set it to oscillate, fixed in, no damping, highest tension. Okay, so let's do that. Let's set it to oscillate. Whoops, hang on, I'm not quite ready for you to go yet. Okay, no damping, highest tension, and okay, good. And then I told you to set the frequency to 83 Hertz. So hopefully you did that. So let's take it to 83 Hertz. Okay, so it's at 83. All right. And so when we hit go, what we see is that the wave starts out, you know, just kind of a nice calm wave. But as time goes on, the wave traveling to the right and the wave traveling to the left, they interfere constructively in certain places and destructively in other places. And this wave goes wild. Okay, so it's off the charts here. What's happening is it's resonating. So this frequency just happens to match the natural frequency of the string. And if we go with any other frequency, so instead of 0.83, let's take it down to 0.7. So that's not much of a change, right? 0.77, 0.83, they're pretty close together, right? That's not going to make any difference, is it? Well, turns out it will. Hang on a sec, I need to sneeze. Sorry about that. Okay, so you see it's trying to resonate here. You can see it almost made it to resonance. Oh, but then it didn't quite make it. So now it's gone back low again, getting some weird stuff. Okay, here it goes again. Okay, it's going to try to resonate. Looking good. Maybe it's going to resonate. Come on, you can do it. Nope, it's not making it. Okay, so it almost resonated, but not quite. So it only resonates if it's at the natural frequency. Right now, it turns out that there's more than one frequency that we can get resonance at. Okay, so what's Aurora say? So Aurora is saying that when she practices clarinet and something in the room resonates when she does long turns. Okay, so keep that in mind. We're going to come back to that. So what Aurora is finding is that when she practices her clarinet, there are some things in her rooms. I don't know what those are. Maybe there are certain cabinets, or maybe it's a window or something. But the frequency of this other thing just happens to match the frequency of the note that she's playing. And yes, what she gets is resonance. That's very cool. Okay, so what if you played with this the way that I asked you to, then what you found was that 0.83 was not the only frequency that resonated. If we take it up to 1.25, that one also resonated. Okay, so let's just take it up to 1.25. Okay, and let's reset it. And then let's say go. Okay, so it starts off nice and good, but oh, it's getting bigger still. And there it goes. It's off the charts. It's resonating. Okay, whereas if we were to be just a little bit lower than 1.25 or a little bit higher than 1.25, then it wouldn't resonate. Okay, so if we look at the pattern here, let's start it going in. Let me slow it down. And then what I'm going to do is I'm going to stop it right there. Okay, so if you look at what's happening when this thing resonates, what you see is that sometimes it goes like that, and other times it goes like this. Okay, but this point right here is always a node. And this point right here is always a node. And of course, the endpoints are always nodes too, by definition, because the string is fixed there. Okay, so what we get is a wave that has two nodes in the middle, and not counting the nodes at the end. And what we have is an antinode here, here, and here. So we get three antinodes and two nodes in the middle. Okay, so if we go back to our original frequency that we started off with, so that was 0.83, right? So let's take it back to 0.83 and let's restart it. And okay, so we're back in slow motion. Let me take it back to normal speed. Okay, so it's starting off. Okay, it's starting to resonate, getting bigger still. And there she goes. The Tacoma Narrows Bridge has just fallen down because we are resonating. But let me put it in slow motion. Okay, and bingo. Notice having trouble stopping it right where I want to stop. Let's try that one. Okay, that's as good as we want. Okay, notice this time we only have one node in the middle. Okay, we got a node right there. Last time we did it, we had two nodes in the middle. This time we had one node. And then here's an antinode and here's our other antinode. And then of course we have nodes at each end. Okay, now the node over on the left side is a kind of a funny node, because if it was a real true node, it would look like this. It would be totally fixed. In this case, it's actually moving up and down slightly. So it's not a 100% node, but it functions as a node. There's no way that it's ever going to go wild like that. Okay, so I'm wondering, is this the lowest frequency that would resonate? Or maybe if we go a little bit lower, maybe we can find another node that will resonate. Okay, and so I'm going to just take this 0.83 here and I'm going to divide it by 2 because I happen to know something that you don't. Okay, so what is 0.83 divided by 2? Well, though that'd be 0.41 or 0.42. Actually, it's 0.415, but okay, so either 0.42 or 0.41. So let's go with one of those. Let's try 0.42 and let's see what happens. Okay, so here it goes. And let's go back to normal speed again. Okay, so it's going up and down and up and down. So it's getting bigger. Yay, it looks like it's resonating. Yep, okay, it is resonating. And what do you notice this time? We don't have any nodes in the middle this time. All we have is an antinode. So let me stop it right here. There we go, okay. All right, so you'll see that this time we have something really interesting. So sometimes it goes down there, sometimes it comes up here. So in the middle, what we have is an antinode. Now, of course, we have a node at each end. Notice we always have a node at each end, which is not surprising because the string is fixed there. So of course we're going to have a node there. And there's no other possibility. The string is fixed. Okay, so what we have is basically the same thing that's happening to the sound wave in the Coke bottle. Except this time it's not a sound wave in a Coke bottle. This time it's a wave on a string. So this could be a guitar string, could be a violin string. And so this frequency that we have right here, this is in fact the lowest frequency. If we were to play around with this thing, which by the way, I encourage you to do, you will find that if you go to a lower frequency, you will not get anything that resonates. What'll happen is you'll go back to those cases where it'll look like it's almost reaching resonance, but then it'll lose it. Okay, so the lowest frequency that can resonate inside in this string, this is what we call the fundamental frequency. And I'm going to call it F0. And so for this string right here, F0 is 0.42 hertz. That is my fundamental frequency. But it's not the only frequency that can resonate. What we saw earlier was that there are other frequencies that could also resonate in this same string, and those are called harmonics. Are these terms that sound familiar to those of you that study music? Have you in your music studies, do you talk about harmonic frequencies? Yeah, okay. All right, so the first harmonic frequency up above the fundamental, okay? All right, so the fundamental frequency, I'm going to call that F0. Although not all books do that. Sometimes some books, they like to call it F1. So don't be surprised if that notation changes. But so I like to call it F0. All right, so that's the fundamental. So if you have a wave on a string, then the first harmonic frequency higher than that, well, we just found experimentally that it was 0.83, which interestingly enough happens to be 2 times what the fundamental frequency was. Okay, and then remember what the frequency was. There was the harmonic frequency that was higher than that. That's what I like to call F2. That was 1.23. Well, hey, isn't that interesting? That number just happens to be 3 times whatever the fundamental frequency was. Okay, so what that means is when you have a wave in a string, so let's call it a string instrument. So those of you that are in the orchestra, you know that there are wind instruments and there are string instruments. So string instruments are things like guitars and violins and violas and, you know, that kind of thing. So with a string instrument, the way it works is that this is what the waves look like that could possibly resonate in that string instrument. So Sam is saying that no one likes the viola, huh? Okay, well, yeah, I like violas, so count me in for one. All right, so what we can do then is we can experimentally determine what the frequencies are. So we found that this one was, so this frequency was 0.8, no, it wasn't 0.8, it was 0.4. So it was 0.42. This frequency was 0.8, actually 0.84. I mean, so if we round off, okay, and then so this frequency up here, this was about 125, 126, okay, or 1.25. So, all right, so what we can do then in your homework tonight is that we're going to use this information to find out everything that we want to know about the string. So like, for instance, let's suppose that this is a guitar, and I don't know, how long is a string on a guitar? Maybe about 1 meter, a little bit long, maybe that's too long. So let's say that this length here is 0.9 meters. All right, so we've got some musical instrument and the length of the string is 0.9 meters. And so experimentally, we discover that the fundamental frequency, the lowest frequency that will resonate on that guitar string, works out to be 0.42. So in your homework tonight, they are going to ask you, okay, so what is the speed of the wave that is traveling in that string? So remember, whenever you have a standing wave here, what's happening is you've got pulses that are traveling from left to right, and they hit the end and they bounce back, and then they travel right and left. So these pulses and these pulses, they interfere with each other in such a way that wherever you have an antinode, they're always interfering constructively. Wherever you have a node, they're always interfering destructively. And if you're at one of these magic harmonic frequencies, then this spot right here will always be a constructive interference. This spot right here will be destructive. Whereas if you go to a higher harmonic frequency, then the constructive is always going to be here. Okay, but these waves are moving left and right, and they're moving at a speed v. So in your homework tonight, what they will ask you to do is they will ask you to calculate, okay, what is the speed that it's traveling at? Well, remember the equation that I told you is going to be your favorite equation. You're going to use it more than any other equation between now and the end of the year. Okay, so this is everybody's new favorite equation, lambda equals V over F. So we know what F is. So if we look, so tell you what, let's focus our attention on the fundamental frequency here. So the fundamental frequency was 0.42 hertz. And so we're looking to find out what a V is. So if only we knew what lambda was. Well, we know what L is. We know that the length of the string is 0.9. So that means if we start here at one node and we go till we get to the next node, we know that that is 0.9 meters. So the question is that the wavelength or is it not? So tell you what I'm going to do here. Let me open up a whiteboard. And let's draw a generic wave. Okay, so here's a generic wave. Okay, but you'll notice that what I've drawn is more than just one wave. I've drawn a couple of them. So if I were to just draw one wavelength only, so I start at a node, and let me do this in a little bit thicker pen here. So I start at a node, I go to the antinode, and I keep on going. So if I stop there, have I moved one full wave? So I want you guys to type in the chat box, yes or no. So if I stop right there, I want you to say yes or no, have I traveled for one full wave? Okay, it looks like you guys are in agreement, no. Okay, I have not. Okay, in order for it to be one full wave, I need to go all the way down and back. Okay, now I've got a full wave. Okay, so if I start at one node and go to the antinode, and if I stop here, so this is where I stop, then I have only gone for half of a wavelength. Okay, so now knowing that, so let's go back now to this thing here. So if I start, whoops, I keep forgetting whenever I change things, I have to turn off annotation and turn it back on. So if I start here at a node, go to the first antinode, stop at the next node, this is only half of a wavelength. So L here is equal to half a wavelength. So what that means is that lambda is equal to 2L. So if I go back into our equation where we say that lambda equals V over F, okay, so we know what F was, at least for the fundamental, the fundamental frequency was 0.42. And so we know that lambda is 2L. So this is 2L, okay? And we know what L is. L, I think the number I said was 0.9, right? Okay, so 0.9 is L. And so then, so all we have to do is then take this and rearrange it to solve to get for what V is. So V then is going to equal F times lambda, which in this case is going to be F times 2L. And so when I do that, so let's see. So I get F, which was 0.42 times 2 times L, which is 0.9. Okay, so when I do this, I find out that this wave speed, this moving left and right, is 0.756, whatever units it is. We measure speed in, and so as long as we're putting the numbers in standard physics units, they're going to come out in standard physics units, meters per second. Okay, so that is the speed of the wave that's traveling. And when we talk about the wave here, we're talking about these pulses that are traveling left to right and right to left. That's the velocity we're talking about. So on your homework tonight, they're going to ask you stuff like that. Okay. Now, let's go back to my online simulator here. Okay. Those of you that play musical instruments, you know that at the beginning of any concert, you always have to tune up your violins and your violas and whatnot. And so what do you do if you're at the beginning of a concert, you know, the concert has not yet started and everybody's tuning up, and you notice that your violin is slightly out of tune compared to everybody else's? What do you do to the violin in order to make it so that it matches the tone of everybody else's violins? Somebody want to unmute yourself and tell us that?
You tune the string by tightening it if it's flat, or
Aha.
loosening it if it's sharp.
Okay, so if the tone of your violin is lower than everybody else's, you tighten up the string. If, on the other hand, the tone of your violin is a little bit higher than it should be, you loosen up the string. So what does that do? When you tighten or loosen the string, what you're doing is you are changing the tension of the string. You are changing the properties of the medium. That changes the speed of the wave. And that in turn is going to change the frequency of the wave. Okay, so let's go back to this thing right here. So remember how we said that if we're at 0.83 hertz, that's when we get resonance. Okay, so let's change everything back to 0.83. Okay, and let's start it going. And let's go back to normal speed here. Okay, so there's our wave. It's starting to resonate and off it goes. Okay, yep, it's going crazy, so it's resonating. Okay, but the frequency that it's resonating at, let's say we don't like that frequency. So what we're going to do is we're going to change the string. We're going to make it less tight. Okay, now that means that our string is not going to vibrate at the same frequency anymore. So let's see if we still get resonance now. So what we did, well, let me just make sure everybody fully understands this. So we changed the tension, which changes the speed. And so so if lambda equals V over F, okay, so that means F then equals V over lambda. So lambda is the same as it was before. I mean, the distance from this end to that end, that hasn't changed. So lambda is the same, but by changing the tension, that changed the properties of mediums. So that has changed. And so that means that our frequency has changed. All right, so let's see if this 0.83 is that, if that's still the resonant frequency now. So here we go. Okay, there's our wave. Okay, it's trying to resonate. Oh, but it's not making it. Oh, okay, no, it's, and now it's losing it, going back down. Okay, so it's trying to resonate, but it's just not quite making it because the frequency is no longer the correct frequency for this particular situation. So what we've done is we've tuned our violin by changing the tension of it. Okay, does this make sense? Good. All right, so Aurora just said that for wind instruments, if you want to tune the wind instrument, you can't go tightening the string because you don't have a string, right? So in what's happening in a wind instrument is a little bit different. Okay, In fact, let's go ahead and let's take a look at what's happening in a wind instrument. So let's go back to my PowerPoint here. Okay, so this is what's happening in what we call a wind instrument. So the classic example of a wind instrument is the Coke bottle, but an organ pipe is also basically the same thing. Organs work the same way as my Coke bottle does. When you play a note in an organ pipe, it blows sound across here, and only one of the frequencies is going to resonate, and which one resonates depends on what the length of the pipe is. Okay, so let's see if we can understand what's happening here. So as we blow air across the top of the Coke bottle or the organ pipe, so we got all those different frequencies. Okay, so what's happening is that these high pressure pulses. So this, what you see right there, is supposed to represent a high pressure pulse. So this high pressure pulse, it rushes down here. Now, there are two types of wind instruments. There are what they call closed pipes, and there are what were called open pipes. So let's focus our attention just on closed pipes right now. A closed pipe means that this end of the pipe here is sealed, whereas an open pipe means that it's actually open to the air. So we'll come back, we'll talk about these a little later. Right now, let's focus our attention on just closed pipes. So when this pressure pulse comes down here, it hits the sealed end. And so we build up a lot of high pressure right at the end, and then it bounces back. So if I were to graph what's happening here, okay, so I've got this pressure pulse that's traveling down here. When it hits the end, I get a high pulse, and that reflects back. This is different from a string. When we had a string, so if I were to graph what's going on here with the string, we always had a node at the end. But in this case, what's happening at the end is that's when we get the very highest pressure. So what that means is at the end here, instead of having a node, we're going to have an antinode. And so if I were to draw that, it's going to look like this. Okay. And again, don't look at this. And even don't look at this. We're just focus all your attention only on this right now. Okay. So what you're seeing inside the pipe here is a representation of the pressure as we get our standing wave inside here. And so if this is a closed pipe, so that means this end is sealed. So what it means is at the end here, we are always going to have an antinode. And that's why it has to work, is because as the pressure waves rush down the tube, when it hits the end there, by definition, that's always going to be an antinode. Anetanode, boy, that's terrible. Let me try that again. Okay, so I don't want an anetanode. I want an antinode. Okay, and again, remember, everything I'm talking about is only about this guy right here. Now notice that up at the top here, the open end, what I have there is a node. And the reason I have a node there is because this open pipe is open to room pressure. So when the sound wave comes up here, when it gets to this point here where it's open to room pressure, well, it might try to make the pressure at that point be higher, but it can't because it's open to the room. And so what's going to happen is the wave is always going to be room pressure when it's at the end that's open. And it's always going to be the highest that it's ever going to get when it's down at the bottom. So that means we're going to have a node at the bottom and a node at the top. All right. And so what you're seeing here is a representation of the lowest frequency wave that can possibly resonate inside this wind instrument. Now that it's not the only one that can resonate. If I come down to here, let's see, let's go to a closed pipe. Okay, so again, here is a closed pipe, but you'll notice that we've got additional frequencies that could also resonate in the closed pipe. And these additional frequencies, these are the ones that we call harmonics. Okay. Whoops, sorry, didn't mean to do that. Let's try this again. Okay, so this is what we call a closed pipe. Now, when we call it closed pipe, please don't get confused by that. It has to be open at one end. So when we say closed pipe, we're talking about the other end. If it was closed at both ends, then no music would possibly get out. So a closed pipe is actually open at one end, but closed at the other. Okay, so some musical instruments are like this, and other instruments are open up at both ends. All right, so here is a picture of the lowest frequency wave that could possibly resonate. Here is a picture of the next higher frequency, the one that I like to call the first harmonic. And then here is a picture of the next highest frequency. This is what I like to call the second harmonic. So these are the waves that could possibly resonate in this tube. And these are the only ones, at least at these frequencies. Now, if you go up higher still, you can get a third harmonic and a fourth harmonic and a fifth harmonic. But you know, that's higher. Let's not worry about those. Okay, so let's do a problem like you might see in the homework tonight. So in the homework tonight, they're going to say, okay, we've got a pipe like this is an organ pipe. And let's say that the length of this pipe is, oh, I don't know, let's say it's 0.75 meters. And so in your homework tonight, they're going to ask you, so what is the fundamental frequency? What is the lowest possible frequency that you could get to resonate inside of this pipe if it's what we call a closed pipe, which means it's open on one end but closed at the other? So here's the way that you do it. Okay, so you asked yourself, how much of a wave are we looking at? All right, so if we go back to our picture of a generic wave and we say, okay, well, one full wavelength, we start at a node, and so we go up to an antinode, and then we come back to a node, we go down to an antinode, and we come back to a node again. So this is one full wavelength. But that's not what we have. We start at a node, so that's here. And notice we stop when we get to the first antinode. So this is all we have in there. So how much of a wavelength is that? Is that half a wavelength? Is that a third of a wavelength? How much of a wavelength is that? Calvin, what do you think? How much of a wavelength is that?
One?
Well, one
Like
wavelength
from
is,
the bottom?
yeah, if we start at a node and we stop at the antinode, okay, so we start here and we stop here. So a full wavelength is this much, but we've only got this much. So we clearly do not have a full wave. A quarter? Okay, you guys all agree? Okay, so if this is the case here, what we've got is a quarter of a wavelength. Okay, so what that means then is that for us, if we're talking about this wave, so L is lambda over 4. And so if we were to rearrange that, let's multiply both sides by 4. So lambda then is equal to 4L for the fundamental wave. Now for these guys, it's going to be different. But for the fundamental wave, lambda is 4L. All right, and we know what L is. L is 0.75. So what we can do then is we can take everybody's favorite equation, everybody's new favorite equation. So we're going to take, we're going to say, so lambda equals V over F. But we want to know what is F. In the homework, they're going to ask you that. So if we swap places with these guys, so F equals V over lambda, but we just got through saying that lambda is equal to 4L, right? Okay, so that means that F equals V over 4L. We know what L is. Oh, but what is V? What is V? Now, a couple minutes ago, we were talking about a violin and a guitar. So what was happening with a violin and a guitar? In fact, tell you what, let me go back to here. So when we were talking about violins and guitars, the waves that were resonating were waves in the string. Okay, so we had a wave traveling this way and it hits the end and it bounces back. So when we were calculating V for a guitar, this was the medium that was carrying the wave was the string. But for a wind instrument, it's different. For a wind instrument, what we've got is something like this. So this is the pulse that's traveling down and then it hits the end and then it bounces back. What is the medium that's carrying the wave in this case? Well, it's air. We don't have a string anymore. We have air. So the speed of a wave in air, well, that's just the speed of sound. So if you're at room temperature, that's 343 meters per second. Now, if it's a cold day, then it's going to be a little bit different. Okay. And if you're at high altitude, it's going to be a little bit different. But so for everything that you're going to do in tonight's homework, you can assume that it's room temperature unless they tell you otherwise. And you can assume that you're at sea level unless they tell you otherwise. So for a wind instrument, V is always going to be 343. And if you don't like the tone that you're getting, if you're playing in an orchestra and you're warming up before the orchestra starts, if you don't like the tone of your clarinet compared to everybody else, you don't have a string that you can tighten. Okay, the speed of that wave is going to be 343 no matter what you do. So if you want to tune up your clarinet, then you have to do what Aurora said in the chat box a few minutes ago. Instead of tightening up your string, you have to slightly change the length of your clarinet. That's the only way that you can do it. Okay, so let's go to your homework problem like tonight. Okay, so if we have, so let's have a closed pipe here. Okay, so let's say that in your homework tonight, they tell you that you've got a closed pipe. So that means it's open on one end and closed on the other. And if they tell you that the length of the pipe is 0.75 meters, and they ask you what is the fundamental frequency, well, you recognize that if the fundamental frequency, lambda, is going to be 4L. And if you take everybody's favorite equation, lambda equals V over F, if you solve that for F, what you get is F equals V over lambda, which is V over 4L. And so there you go. And so you take that number for L, stick it in there. You take 343, you stick it in for V, and it'll tell you what the fundamental frequency is. So let's just do it just for grins here. So if we have an organ pipe that is 0.75 meters long, then the fundamental frequency is going to be 343 divided by 4 and also divided by 0.75. And what we'll get is the fundamental frequency is going to be 114 hertz. Okay, that's the kind of homework problem you're going to have tonight. Now, what they're going to do then is they're going to follow that up and they're going to say, okay, but what about the first harmonic frequency? Because this fundamental is not the only frequency that can resonate in there. We could have one of the harmonics in there. So let's look at that. Okay, so let's suppose that we want to know what is this frequency. Well, this frequency could also resonate in that same tube. So if we start at a node and we go to the first antinode and then we go to the second node and then we stop when we get to the other antinode there. So how much of a wave is that? Okay, so let's go back to here. So if we go a full wave, so this would be a full wave, right? But that's not what we have here. We started at a node, okay? And then we went to the first antinode, and then we went to the second node, and then we stopped when we got to the second antinode. Okay, so if this distance here is lambda, but we stopped when we got here, then how much of lambda do we have inside of there? Answer, we have 3/4. So L is equal to 3/4 of a wavelength. So if we were to rearrange that, if we solve for lambda, so if we multiply both sides by 4/3 in order to solve that, so what we're going to get then is that lambda is going to be equal to 4/3 times L, which is what you see right here. And so then when we solve that, when we put that into everybody's favorite equation, lambda equals V over F, and we solve that for F, what we're going to find is that the frequency of this first harmonic wave is not going to be V over 4L. It's going to be 3 times V over 4L. So in other words, it's going to be 3 times what our fundamental frequency was. And if we do the same thing for this next one, we'll find out that our next harmonic frequency is going to be 5 times whatever our fundamental was. And the next one after that is going to be 7 times the fundamental. The next one after is going to be 9 times the fundamental. Okay. So this is how wind instruments work if they are what we call closed pipes. Now, it turns out that that's not the only kind of wind instrument that we could have. We could have a wind instrument that looks like this. Okay. This is what we call an open pipe resonator. Okay. So when we say open pipe, what we mean is that it's open at both ends. So not only is open at the top, but it's also open at the bottom too. So like for instance, a flute. This is the way that a flute would be. It's open on both ends. So you'll notice that the mathematics are a little bit different here. So in this case, lambda is not going to be L over 4 anymore. This time, lambda is going to be lambda is not going to be 4L anymore. Lambda is only going to be 2L this time, because if we start at a node and end at a node, so again, so here's our wave, right? So if we start at a node and we end at a node, so what we've got there is not lambda, that's lambda over 2. Okay, so then what we have in here is lambda is going to be twice the tube length, whereas previously lambda was 4 times the tube length. So what that means is that the formula we use to calculate what our fundamental frequency is going to be different. So instead of having that our fundamental frequency is V over 4L like it was before, now it's V over 2L. So tell you what, let me flip back and forth. So what you're seeing right now is an open pipe. And so there's the closed pipe. So for a closed pipe, the fundamental frequency is V over 4L. For an open pipe, the fundamental frequency is V over 2L. See the difference there? Now, things get really interesting when we look at the harmonics. Okay, so let's look at the harmonics. So if we have an open pipe instrument, then the mathematics for an open pipe says that our first harmonic frequency is going to be twice what the fundamental frequency was. Now that's different than one we had before. Remember, before we said that the first harmonic was 3 times the fundamental, but with an open pipe, it's different. With an open pipe, it's only 2 times the fundamental. Okay, and then same thing with the closed pipe. The second harmonic frequency was 5 times the fundamental, but if we go back with an open pipe, you'll see that the second harmonic is only 3 times the fundamental. So make sure that you guys work through the example. Make sure you read the book. I think the book did a really good job of explaining this, but you guys need to read through it. So the behavior of a wind instrument is very different depending on whether it's open at both ends or if it's open on one end but closed at the other end. Okay. So when you do the homework tonight, make sure you pay very close attention. Is it an open pipe instrument or is it a closed pipe instrument? Or the other possibility is that it might be a stringed instrument. Okay. Okay. So I realize I've hit you with a lot of stuff, but hopefully it makes sense. Yeah. So give me some yeses and nos in the chat box here. If this made sense to you, please type in yes. If it didn't make sense, type in no. And if it's a no, then let's see if we can do anything to help clear up your thing. So everybody so far is saying yes. Now you can please type it in as a private message, especially if it's a no. I don't want you to make it, I don't want you to embarrass yourself with a public no. All right, so I'm seeing yes. Okay, there's a no. Okay, finally, thank you for being honest. Okay. So, okay, and somebody just typed something really interesting in a private message. So somebody just said that they found that what works for them is to go after the class is over, go back and watch the recorded video a second time. So the first time through, maybe it didn't make quite as much sense as you would like, but the second time through, then it makes more sense, especially if you read the book and then come back and watch it the second time. Okay, so so I just had one person ask me if I could go back to the last slide real quick. Okay, so let's go back to this slide right here. Okay, so this is actually 2 slides that I'm going to toggle back and forth between really quickly. Okay, so up at the top here, you notice what we have here is an open pipe. And down here, this is the formula that tells you the frequency for what we call the fundamental. Okay. So this lowest frequency is what we call the fundamental frequency. And these other frequencies, these are called harmonics. Okay. So notice how this works. Okay. So if it's an open pipe resonator, we use this formula to calculate the fundamental frequency. And if it's an open pipe resonator, then the next harmonic up after that is going to be twice the fundamental. And the next one after that is going to be 3 times the fundamental. Now compare that with what happens if it's a closed pipe. Okay, so with the closed pipe, notice the frequency is, the formula for the fundamental is a little different. Instead of V over 2L, it's V over 4L. And also notice that the pattern for the harmonics is different. Instead of the first harmonic being 2 times, and then the next harmonic being 3 times the fundamental, if it's a closed pipe, the first harmonic frequency is 3 times, and the next harmonic up after that is 5 times, and then 7, and then 9, and then so forth. Okay, so make sure you understand this pattern. Okay, closed pipe, open pipe, closed pipe, open pipe. Okay, so hopefully that cleared things up for you. Okay. All right, well, it's almost quitting time. So I guess you probably want to know what the homework is. Now you of course know that you can go on Canvas and just look on Canvas. So here is the homework. I want you to do problems 18 through 21. And then at the end of the chapter where they have a couple extra little practice problems, I want you to go back there and I want you to do problems 77, 78, and 80. Okay, and then of course, don't forget the daily quiz. All right, so that's your homework tonight. If you have no questions, then you can go ahead and type bye into the chat box and I will see you next time. And if you do have a question, but you didn't want to ask it because you knew it was being recorded, let me go ahead and turn off the recording and then we can talk in private.